When you look up at the moon, it always seems the same, doesn't it? The same craters, the same dark patches, the same familiar face staring back at us. It doesn't matter if it's a summer night, a winter evening, or a photo from decades ago, you always recognize it. This brings up some big questions. Is the moon actually spinning like Earth, or is it just sitting there, completely still? And what about the famous dark side of the moon? Is it a real place where sunlight never reaches, or just a myth from movies and songs? In this video, we're going to dive into these questions and figure out what's really going on. You'll discover that the moon does spin, there's no side that's permanently dark, and it's all because of a cool phenomenon called tidal locking. This is the result of billions of years of gravitational tug-of-war between the Earth and the moon. And you'll see this isn't just a special thing for our moon, it's actually pretty common throughout the solar system. The key to solving this mystery is understanding that the moon has two main motions. First, there's rotation. The moon spins on its own axis, just like Earth does. But while Earth takes about 24 hours to complete a spin, the moon takes about 27 days. The second motion is its orbit. The moon travels around the Earth in a roughly elliptical path. And here's the kicker. The time it takes to complete one full orbit is also about 27 days. Because these two times are almost exactly the same, the moon rotates on its axis at the same rate that it orbits the Earth. From our perspective, this perfect timing means we always see the same side. Think of it like a dancer moving around a partner. The dancer keeps turning, so their face is always looking at their partner. The partner only ever sees the dancer's face, even though the dancer is both moving around them and spinning at the same time. Many people think we see the same side because the moon isn't spinning, but it's the exact opposite. The fact that we always see the same face is proof that it is spinning just in perfect sync with its orbit. You can even try a simple experiment at home to see this for yourself. Put an object, like a bottle, in the center of a table. That's your Earth. Now grab a ball to be your moon. First, walk the ball around the bottle, but don't spin the ball at all. If you put a little sticker on the ball, you'll see that from the bottle's point of view, the sticker appears and disappears. The bottle would see different faces of the moon. Now, do it again. This time, as you move the ball around the bottle, slowly spin the ball so the sticker is always facing the bottle. If you were sitting where the bottle is, you'd see that the sticker never disappears. It's always looking right at you. But from an outside view, you'd see the ball has completed one full spin during its orbit. That's exactly what's happening with our moon. It has adjusted its rotation to always keep the same face pointed toward us. So far, we know what the moon does, but we're missing the most interesting question. Why did it end up like this? The explanation lies in gravity and what are called tidal bulges or solid tides. Earth's gravity doesn't act uniformly on the entire moon. The side closer to Earth feels a slightly stronger gravitational pull than the far side. This difference stretches the moon just a little, creating small bulges aligned roughly along the Earth-Moon direction. It's similar to what happens on Earth's oceans, where the moon's gravity generates tides. On the moon, because it's solid rock, these bulges are accompanied by internal friction. Scientific models show that when the moon formed, it was spinning much faster. Over time, these bulges, constantly being pulled by Earth's gravity, acted like a brake. They transformed the moon's rotational energy into internal heat. This braking process gradually slowed the moon's spin until it reached a special state where its rotation period matched its orbital period. At that point, the system became stable. The moon was tidally locked, always showing the same hemisphere toward Earth. Breaking this equilibrium would require a huge disturbance, something that hasn't happened for billions of years. Now that you understand tidal locking, we can clear up a famous myth, the so-called dark side of the moon. Many people think there's a hemisphere of the moon that never receives sunlight, always in total darkness. That's false. The moon, just like Earth, gets sunlight on different parts depending on its orientation. What does exist is a far side, the half of the moon we never see from Earth. When the near side is lit and we see a full moon, the far side is in darkness. And when we see a new moon, with the near side almost completely dark. The far side is the one receiving sunlight. In other words, both hemispheres take turns being illuminated. So next time someone says dark side, remember the correct term is far side. For most of human history, the far side was a total mystery. That all changed with the space age. When robotic probes started orbiting the moon and taking pictures, they revealed something surprising. The far side is very different from the side we see. The near side has large, dark regions called maria, vast plains of solidified lava. On the far side, those maria are much less common. Instead, it's dominated by heavily cratered highlands, with way more visible impact marks. This suggests the geological histories of the two hemispheres weren't the same. There may be differences in crust thickness or how giant impacts affected each side. Thanks to these missions, we now know the moon as a body with two very different faces, even though from Earth we only ever see one. Let's imagine for a moment an alternate universe where the moon never became tidally locked. If its rotation were faster than its orbit, from Earth we would see the moon slowly showing us different areas of its surface over the months. Instead of having a single familiar face, we would have a changing map of craters and maria rotating in front of us. Ancient human cultures, instead of building stories around one consistent face of the moon, would have had to interpret a disk that changes much more dramatically over time. Also, the Earth-Moon system would have slightly different tides and a different transfer of angular momentum, because tidal braking would still be working to synchronize the two periods. Over extremely long time scales, even in that imaginary scenario, the natural tendency would still be for the rotation to slow down and eventually reach another tidally locked state. In short, what we see today, a moon that always shows us the same face, is not a random coincidence, but the expected result when gravity is allowed to work for billions of years. Tidal locking is not a rare quirk unique to our moon. It is actually quite common in the solar system. Many moons of the giant planets are also tidally locked to their planets. For example, Io, Europa, and Ganymede, three of Jupiter's most famous moons, always show the same hemisphere to Jupiter, just like our moon does to Earth. Around Saturn, several moons are also locked in the same way. Even in the Pluto system, Pluto and its moon Charon are in mutual tidal lock. Not only does Charon always show the same face to Pluto, but Pluto also always shows the same face to Charon. If you were standing on Pluto's surface, you would see Charon always in the same place in the sky, motionless, like a giant geostationary satellite. These examples show that tidal locking is a natural consequence of the game between gravity, rotation, and time, and that what we observe with our moon fits a general pattern in orbital mechanics. Now you can answer correctly when someone says that the moon does not spin, or that it has a mysterious dark side. You know that the moon does rotate on its axis, that its rotation period and orbital period are almost exactly the same, and that this makes it always show the same face to Earth. You also know that Earth's gravity, through tides and internal friction, slowed the moon's rotation over billions of years until it became tidally locked, and that there is no eternally dark face, only a far side that also receives sunlight, and that we know thanks to space probes. And you have seen that this tidal locking phenomenon is common for other moons in the solar system, and even for systems like Pluto-Charon. If you would like the next video to be about what would happen if the moon were released from this lock and started showing us all its faces, let me know in the comments. And if this video helped you understand our cosmic companion, the moon, remember to like, subscribe, and share so more people can discover the real science behind what we see in the sky.